You know, black holes are probably one of the strangest, most nonsensical things in the entire universe. They just seem to break all the rules. So, all right, let's dive in and try to actually make sense of them.
In this explainer, we're really going to tackle two huge questions. First off, where did these things even come from? I mean, what kind of cosmic event is powerful enough to create one of these monsters?
And then, of course, the big one, the question we've all thought about. What would actually happen if you took that one-way trip into the abyss? Let's just say the answer is way, way stranger than you can possibly imagine. To get how a black hole is born, we have to start at the end of a truly massive star's life. See, a star's whole existence is this incredible balancing act that, well, eventually ends in total catastrophe. Think of a giant star as a constant tug of war. Deep in its core, you have nuclear fusion, which creates this tremendous outward blast of energy and radiation. That pressure is pushing out, while the star's own immense gravity is trying to crush everything inward. For millions, sometimes billions of years, these two forces are in a perfect, delicate balance. So, as the star gets older, it starts fusing heavier and heavier elements in its core. It goes from hydrogen to helium, helium to carbon, all the way down the line. But eventually, that process hits a brick wall. And that wall is iron. See, unlike all the other elements, when you try to fuse iron, you get nothing. No energy comes out. The furnace at the heart of the star just goes out. And that's when things get really violent. With that outward push from radiation gone, gravity wins. And it wins instantly. The entire core collapses in on itself, and the rest of the star comes screaming inward at a quarter of the speed of light. All of this triggers a supernova, an explosion so massive it creates all the heavy elements in the universe. And what's left behind? Well, if that original star was massive enough, the core keeps collapsing forever, forming a black hole. So, we've made a black hole, but what is it? What's it actually made of? Let's break down its two main, totally mind-bending parts. First up, you have the event horizon. This is what we kind of think of as the surface of the black hole. But it's not solid, it's a boundary in space-time itself. It is the ultimate point of no return. And here's why that matters. To get away from the event horizon, you'd have to go faster than the speed of light. And since that's, the universe's ultimate speed limit, nothing can do it. Not even light. And that's the black part of the black hole. It's a sphere of perfect darkness because the light inside can't get out. Now for the whole part. Right at the very center, we think there's a singularity. This is where all the mass of that original giant star has been crushed down into a single point. A point with basically zero volume and infinite density. And right here, this is where our understanding just completely falls apart. We honestly have no idea what a singularity really is. Our laws of physics, everything we know, it all just breaks down. It's literally like the universe is trying to divide by zero and just gives up. Oh, and by the way, let's bust a quick myth. Black holes are not cosmic vacuum cleaners. They don't just suck everything up. Their gravity is incredibly strong, yeah, but only when you get really close. In fact, if we replaced our sun with a black hole that had the exact same mass, Earth would just keep orbiting like nothing happened. I mean, we'd freeze to death, obviously, but our orbit would be fine. All right, so what would it actually be like to get near one of these things? This is where our whole concept of reality, and especially our concept of time, starts to get seriously weird. So let's say you're the unlucky astronaut falling in. From your point of view, as you get closer, you'd look out and see the entire rest of the universe speed up like it's in fast forward. You'd watch the future unfold. But for someone watching you from a safe distance, they see something totally different. To them, you start to slow down. You seem to freeze in time right on the edge of the event horizon, get redder, and then just fade away. It's two completely different realities, happening at the exact same time. Wild, right? Okay, so you did it. You crossed the event horizon. From your perspective, you're now inside the black hole. What happens next? Well, scientists have two main ideas, and trust me, neither one is a good way to go. So theory number one is called spaghettification. It's exactly what it sounds like. The gravity is so much stronger at your feet than your head that it stretches you and stretches you and stretches you until you're torn apart into a stream of hot plasma that's just a single atom wide. Theory number two is the firewall. The idea here is that the moment you cross the horizon, you slam into a wall of super high energy particles and are just instantly vaporized.
So yeah, pick your poison. But here's a really weird twist. How long you'd survive actually depends on how big the black hole is. With a small, stellar mass one, the gravity gets intense so quickly that you'd be spaghettified before you even got to the event horizon. But with a supermassive black hole, the event horizon is so huge and so far from the center, you could actually cross it and be perfectly fine. For a little while anyway. And that size difference really brings us to the two main types of black holes out there. You've got the stellar mass ones, which are maybe a few times the mass of our sun, but are only about the size of an asteroid. And then you've got the supermassive ones, the absolute behemoths that sit at the heart of pretty much every single galaxy, including our own Milky Way. And just to give you an idea of the scale we're talking about, the biggest one we've ever found is called S50014 plus 81. It has the mass of 40 billion suns. Its diameter is 47 times the distance from our sun all the way out to Pluto. These things are just almost too big to even comprehend. But for all their power, for how permanent they seem, even black holes don't last forever. They do have a lifespan. And their death? Well, it's going to be one of the very last spectacular events in the history of the entire universe. The secret to how a black hole dies is something called Hawking radiation. Turns out, what we think of as empty space is actually fizzing with these tiny virtual particles that pop into existence and then disappear in an instant. But if a pair of these particles pops up right on the edge of an event horizon, one can fall in and the other can escape. That escaping particle basically steals a tiny, tiny bit of energy and mass from the black hole, causing it to very, very slowly evaporate over time. Now, when I say slow, I mean unbelievably slow. It takes trillions upon trillions of years. But as the black hole gets smaller, the process speeds up. When it shrinks to the mass of an asteroid, it radiates with the warmth of a normal room. When it's the mass of a mountain, it glows with the heat of the sun. And in its final single second of existence, it goes out with a bang, exploding with the energy of billions of nuclear bombs. But don't wait around to see it. The timescales here are just so vast. By the time the last black hole finally explodes, the universe will have already been cold and dark and empty for an unimaginable amount of time. It'll be the final firework in an empty theater. A pretty profound thought about the ultimate fate of, well, everything.